first of all, thank you so much for inviting me. I'm really delighted to present at your seminar. My name is Fabian Klenner. I'm an earth scientist by training, and then I did my PhD in the research group of planetary science and remote sensing at Freie Universität Berlin in Germany. Pretty much a year ago, I received my PhD, and now I'm a postdoctoral researcher in the same research group. And I want to add my piece to the puzzle of the search for life on icy moons in the solar system. And that's actually what I want to talk about today. So first of all, I will introduce you to some of the icy moons in the solar system, tell you a bit about why they are so interesting for life. And then I want to connect this with my own work. So the last 10, 15 minutes, I will talk about my own work. And yeah, this will be my presentation.
Super. Are you part of any astrobiology society already?
Yeah, I am part of the German Astrobiology Association, where I am co-lead of the working group for icy moons and ocean worlds. And I am co-founder of the ABNP Astrobiology Network of Pakistan, together with a colleague of mine and several other people. And yeah, now I'm happy to be here.
Are you part of Blue Marble Space?
No. And I'm also a member of NFOLD, NASA's Network for Light Detection.
All right, that's great. Yeah, I'm thinking about Blue Marble because I think we have their like subgroup that is called Building Astrobiology Communities in the World, and Pakistan. I think someone from there, like Omar, or someone was there. I don't know if you recognize the name Omar. No, okay. Never mind. I think we could integrate a little bit more with our efforts. I'd be happy to track whatever German Astrobiology Society is doing. Do you usually communicate in German or in English?
Usually in English.
That's great. Okay, we could learn from you. So can you add me like to the mailing list or something?
Or should I sure. Myself? So we have we do not have meetings every week or every 2 weeks as you might have, but we meet every few months or so, discussing about icy moons, ocean worlds, progress, and maybe research papers, ideas we have. And of course, if you're interested, I can invite you to that. Sure.
Because you're talking now about your subgroup about icy moons, right? But you said that the whole society, does it even have meetings, like regular
conferences, small conferences, or once a year we have we have a small kind of conference, so people present their work, and it's a small conference.
Yeah, it's good to know what else is going on around us. So thanks for coming.
So sure, if there are news, I can share it with you. Sure.
Super. I'll let you start your seminar right now. Thank you so much. And yeah, we're ready to ask questions after you finish.
All right. So then I start sharing my screen now.
Please leave questions for Fabian on the chat in the meantime.
So can you see my screen, or do you see the presenter's mode?
It looks good.
All right, that's
I still
great.
see your like taskbar from Windows, but all the rest is the presentation. So it has to be like that.
Yeah,
it's new.
All right. Okay, so I already introduced myself, and I want to talk about the icy moons in the solar system and why they are so interesting for the search for life. And in the end, I want to connect it with my own research. And you already see in the background my two favorite icy moons. Just as a spoiler, that's on the left. You see, by the way, can you see my laser pointer?
I don't.
You don't? Okay. Do you see it? Yeah, now you see it. Perfect. Okay, so on the left, you see Saturn's moon Enceladus. On the right, you see Jupiter's moon Europa. So Enceladus is pretty bright. It's apart from the sun, the brightest object in the solar system. So it reflects nearly all of the sunlight that receives. And so we have very, very pure water ice on Enceladus surface. So on the northern hemisphere, you have several impact craters. On the southern hemisphere, you only have a few impact craters, but you have these 4 interesting bluish stripes here. They are called tiger stripes. And on the right, Jupiter's moon Europa, you also have an icy surface, but it's not that bright as Enceladus is. And you also see here these bluish reddish colors that are indicative for chemistry, ongoing chemistry. So it's not pure water ice that we have here. And interesting, for both moons, they have liquid water, not on the surface, but in this subsurface. And they're not the only objects that have liquid water. So for completeness, we have several ocean worlds in the solar system. We have our beloved planet Earth and Europa, Enceladus, and several other objects that have confirmed subsurface oceans, or that the subsurface oceans need to be confirmed. For example, we also have Titan, Ganymede, Callisto, other moons of Jupiter and Saturn. And all these worlds, just by definition as an ocean world, they fulfill one requirement for life as we know it, at least, and that's liquid water. But water is not everything that is needed. So we might need, in addition to water in form of global oceans and a kind of persistence of water, we need energy. We need an energy source. So we can have hydrothermal activity, radiolysis, or whatever. And in addition to that, we would need a kind of chemistry. We need bioessential elements. For example, a chondritic composition of a rocky core that is then somehow in connection with the water and with a kind of energy. And then we might have the 3 main ingredients for life as we know it. And if we now plot the objects that I've shown in the previous slide into this diagram, we see that we have actually 3 moons that seem to fulfill all these 3 requirements. And I want to introduce you now to these 3 moons. I want to start with Titan. It's the largest moon of Saturn. And after talking about Titan, I will, in a bit more detail, talk about my 2 favorite moons, Europa and Enceladus. So starting with Titan. On the right, you first see Saturn. It's a beautiful image. You see here the ring plane, Saturn's ring plane. There's shadows of the rings on the planet. And you see this big object here, and that's Saturn's moon Titan. So it's Saturn's largest moon. Titan is actually the 2nd largest moon in the solar system. We only have Ganymede, a moon of Jupiter, that is bigger than Titan, just 2%. So, and if we have a bit more detailed look on Titan, on this picture, it's pretty dark, but you can already see one speciality of Titan, and this is here. The dense atmosphere. You see light scattering through the atmosphere. That's shown here in this orange color. So we have a very dense atmosphere on Titan, and it's the only moon with such an atmosphere in the solar system. If we now have a bit more detailed look on the interior and the surface of Titan, we have to start with a silicate rocky core inside the moon that is then covered by a high pressure ice layer. So we have a rocky core that is covered by high pressure ice, and above this high pressure ice, we have a subsurface liquid water ocean. And above this water ocean, we again have an ice shell that is then covered by a thick and dense atmosphere with, for example, methane rain. If we then have a look to the surface of Titan, so on the right, you can see a radar image taken by the Cassini spacecraft. And what we see here in bluish, these are also liquids. So we do not only have liquid water in the subsurface, but we also have liquids on the surface. But this is not water, that's hydrocarbons. So we have hydrocarbon dunes and lakes. So we primarily will find methane here in these lakes. So this means actually we could have in the subsurface water ocean life as we know it, that is water-based, or even on the surface, we could have a kind of weird life, or life as we don't know it, life that is hydrocarbon-based somehow. And actually, my personal favorite would be that we somehow have a connection between the hydrocarbon chemistry on the surface with the subsurface ocean water. So if we can somehow connect this to maybe, let's say, meteorite impacts or whatever, and then we might connect this nice carbon chemistry again with water, and we may have a good case for life again. Okay, how to explore Titan? Actually, 2.5 years ago, NASA finally selected a new mission that will fly to Titan. Launch is planned in 2027. This mission is called Dragonfly. So you can see here an artist's Titan, and Dragonfly is a kind of drone. It's a kind of rotorcraft. So this drone will then land on the moon, will do some analysis on ground, then it will start again, will fly a few kilometers, will do in-flight analysis of the atmosphere, then it will land again, will fly again. It's a pretty cool and ambitious concept. And why this works so well is actually that Titan's gravity is so low, it's 7 times lower than Earth gravity, and combined with this extremely dense atmosphere, this makes Titan actually the best place in the solar system for a drone to fly through an atmosphere. And now I want to show you a very quick, I hope it works, a very quick small video about, I hope this will work. It's a minute about, can you give me feedback if it works?
It did for a second. Yeah, it does.
Okay, great, thanks. So that's about the Dragonfly mission. You see Titan. So you have a parachute deployment.
So far, similar to Mars.
Yeah, as second, the main parachute. And that's how the mission is supposed to land. So quite above the surface, we will release the Dragonfly rotocopter. It will then do some in-flight analysis. Will finally land. Do some on-ground analysis. And then it will start again and fly to another place.
Rafael?
Is RTG powered, is that correct?
Yeah.
Okay, now we have talked about Titan, and that's enough Titan for today already, because now I want to focus a bit more on Europa and Enceladus. And I've showed you the interior structure of Titan, and there's maybe one disadvantage if we have a look on the subsurface water. So actually the subsurface ocean is sandwiched by 2 ice layers. So we might not have a contact with a rocky core, but that's the case actually for Europa and Enceladus. So that's a good advantage of these 2 moons. So we have a rocky core that is in contact with the subsurface ocean. And this hot core is a source for heat and also bioessential elements. So we can leach out elements directly into the water. So then we have energy, chemistry, and liquid water all together. And this makes these 2 moons so interesting for the search for life. Let's talk a bit more about Enceladus. Again, we have a nice Cassini image of Saturn. It's the Lord of the Rings with its amazing ring system. You have the Ering. This is this brightish, diffuse, whitish ring here. And when we have a closer look to the Ering, it reveals that we have a tiny moon that's Enceladus. It's a diameter of about 500 kilometers, is orbiting the moon in the brightest spot of this ring, actually. And then the Cassini spacecraft flew by Enceladus, and what it discovered was really, it was amazing. So we saw a plume of ice grains and gas emitting into space just from this tiny moon. So, and we believe that these ice grains that are ejected are connected to the subsurface ocean. So, in principle, we can just by sampling these ice grains, sample the interior ocean and do compositional analysis with that. And also, Enceladus feeds the whole Ering with this ocean material, and that's why this Ering is so diffuse and bright. We can also then talk a bit about Jupiter. Again, there's a small thing, yeah. Again, so we have for Jupiter several moons. We have the Galilean moons Io, Europa, Ganymede, and Callisto, the 4 Galilean moons. Europa is the second innermost one. If we zoom out of Jupiter and zoom out, we see that Jupiter has several other moons, and it looks a bit confusing, doesn't it? But the interesting part here is Europa, the second innermost Galilean moon of Jupiter. And Europa itself also has a subsurface ocean. That is that this ocean has twice as much water as all oceans on Earth combined. So at least what we think. So we also have here some indicated plumes. We have, you see Jupiter in the background. Also here you see Io, the innermost Galilean moon, and there's also kind of volcanism of Io, but this has nothing to do with ice grains or a subsurface water ocean. That's more like sulfur volcanoes, and Io is pretty hot. And there's more and more evidence for Europa to have plumes. So scientists who worked with the Hubble Space Telescope found some evidence for sporadically active plumes. And we also have Galileo data. These were plasma wave observations. And then they also have found some evidence for plumes on this moon. Okay, now we have liquid water on these moons. We might have a plume. So there's an easy way actually to explore the subsurface ocean of Enceladus and maybe also of Europa just by flying through these plumes and analyzing individual micrometer-sized tiny ice grains. And how we could do this, one example was the Cassini spacecraft in the vicinity of Enceladus and Saturn. So you can see here on the right, the Cassini orbiter. These were photos that were taken before the thermal blanket was attached. So you can see all the science instruments, you can see the rocket engines, the reaction wheels, and all the stuff on the spacecraft. And this spacecraft was equipped with several instruments. And one of these instruments was CDA. That's a cosmic dust analyzer. And this was the instrument that was capable of analyzing ice grains that were emitted by Enceladus. It worked in a way that you have these ice grains that are hitting then the instrument target. This process worked like you can see here. You have a tiny ice grain that is hitting the metal target. You have it vaporizes, ionizes. Cations means positively charged ions are generated and accelerated towards the QI and QM detector. And what you find in the end are several signals. And the most interesting one is this QM signal. I can show it again because this generates the data we then get delivered back to Earth. So that's this process here of ionization is called impact ionization. That's an important term here. And in the end, the data that is sent back, these are mass spectra, time of flight mass spectra. And how this looks like will show in my next slide. So that's a typical mass spectrum of an individual ice grain that was delivered by the CDA instrument on board Cassini. So for those who are not familiar with mass spectrometry, the y-axis it's just the signal strength. Actually, the higher the signal, the more of this thing of this species is there. And on the x-axis, you see the mass. And this means that all these signals are representative for a specific mass of a species of a substance that was in these ice grains. You can, for example, see here we have pure water, that's H2O and H+, so we need cations, we need positively charged ions to create these signals, and all these circles here indicate pure water signals. We also have sodium in these ice grains, a bit of sodium here, and all these triangles show sodium signals. CDA itself was only sensitive to cations, so means positively charged ions. We could determine impact rates, masses, speeds, charges, and compositions of the ice grains with a relatively poor mass resolution. So mass resolution means actually just how well are the signals resolved from each other. So for example, here you can clearly see two signals, water and sodium, but if you go to higher masses, we know that there is sodium now, but if you see this the first time, you might think this is just one signal. And this can be quite difficult to analyze this data. And the maximum mass of the species that was recorded was about 200, sometimes a bit more here. Good. Now we jump again to Europa. So we also need a spacecraft on Europa. How to search for life on Europa? There is a spacecraft, the Europa Clipper spacecraft, that is scheduled for launch in October 2024. And Europa Clipper will perform about 45 flybys on the moon Europa over a primary mission duration of 3.5 years. Most flybys will be below 100 kilometers, so that's at some good altitude to detect ice grains that are lifted from the surface or even ejected by plumes. Europa Clipper will fly on a mega trajectory. Mega means a mass Earth gravity assist. So what this means is shown here. So we have the launch of Europa Clipper in October 2024. The spacecraft will start, will have a mass gravity assist in 2025, then go back to Earth orbit, will have an Earth gravity assist in 2026, and then it has enough power to fly to Jupiter. And Jupiter orbit insertion, GOI, will be in 2030. So that's the plan. And the mission will then collect tons of data that will be sent back to Earth and will help, then also will be complementary to ESA's JUICE mission that will just start a year earlier than Europa Clipper, and a potential future Europa lander mission. So one goal also of Europa Clipper is to assess where a future Europa lander could, in theory, land, so which locations are good for that. And yeah, Europa Clipper will be equipped with 9 instruments on board, and one of these instruments will be an impact ionization mass spectrometer. So that's good for us because we can analyze ice grains. And this mass spectrometer works in a similar way as CDA did, but has a much, much higher performance. So we also have a particle that hits the metal target. Ions are generated, are then accelerated, reflected, in the end detected, and we create again these kind of mass spectra. Yeah, in principle, we have we can determine the same properties as with CDA, but we can also determine much better the trajectory of these ice grains, how they entered the instrument aperture because of these very capable entrance grid systems here. And another big advantage of the SUDA instrument, the surface dust analyzer, is that it is not only sensitive to cations, also to anions. So it's anions are the negatively charged ions. It has a much higher mass resolution than CDA, so we can resolve these peaks much better in the spectra, and it records also heavier species up to a mass of 500 atomic mass units. And still, analyzing such data from space can be quite difficult in the end because you just get some data back, but you have to then make a case what exactly you see, what could be in these spectra. You have to assign species to them. And this is how our lab work comes in handy. So what we do in our lab is we simulate these ice grain mass spectra with a method that's called LILBID. It's laser-induced liquid beam ion desorption. It works in a way that we have a very tiny water beam in a size range of a few micrometers that is hit by a pulsed infrared laser. And this infrared laser then hits the tiny water beam, generates cations, anions, neutral molecules, electrons, and we can then separate these differently charged ions, and we can accelerate cations or anions, reflect them and detect them with the detector. In the end, we generate time-of-flight mass spectra and simulate these ice grain mass spectra in space. So how this process looks like when the laser hits the water beam is shown here in this gray figure inlet. You can really see that here a plume of ions is generated. So the laser wavelength we use is 2840 nanometers. It's chosen to excite the OA stretch of the water molecule, so to promote ionization. And we can also detect cations and anions with a much better mass resolution. So the data we have in the lab has a much better mass resolution than we can detect in space, and this helps analyzing the data from space. To summarize this again, we have in space ice particles that hit a metal target, cations or anions accelerated, detected. In the lab, we have a pulsed infrared laser hitting a water beam, and cations or anions accelerated and detected. And the spectra in the end look like this. So again, we have here a CDA mass spectrum with a kind of water signals that are these bluish diamonds here, and also sodium signals that are these green triangles again. And then I went to the lab and reproduced this spectrum as accurately as possible. Also, I mixed a solution, put a bit sodium chloride in it, and then I created this mass spectrum. So what you can see is that so the mass resolution here is much better. So the peaks are much better resolved than in the data from space. And the next, what I want to present you is CDA success story. So the CDA instrument recorded thousands of mass spectra, and analyzing this data revealed several things about Enceladus. And not all, but most of these discoveries required these lab experiments, because in the lab, you exactly know what you mix into your measuring solutions, and you generate the mass spectra. It's much easier to analyze than just having the data from space. And what we found in Enceladus is that a good proportion of these ice grains contains sodium salts. We have sodium chloride, we have sodium carbonate, also cluster species of that, sodium hydroxide, also a bit potassium. And as we believe that these ice grains are formed from the subsurface water ocean, we think that this subsurface water is pretty salty. Another discovery was detection of silica nanograins. So the size range of these grains indicates that there's ongoing hydrothermal activity on the ocean floor in space. So in addition to that, we also found organics. These are complex organic macromolecules. So 79, you have here one species that cannot be explained by water or any salts. This is an benzene cation. This is an aromatic ring structure. It's just organic chemistry. Also, this HMOC series here, you have clear indications of hydrocarbon backbones that are separated and generate these peaks in the spectra. Then we go further, and we also found volatile organic species that are nitrogen, oxygen bearing, have also aromatic ring structures. So, but yeah, despite the detection of various organics, we did not find any biosignatures yet, so means signatures of biology. Okay, so to summarize again quickly, Enceladus core interface, we have a liquid water, salty ocean with organics in them, and with then these tiger stripes in the South Pole that eject ice grains into space. And if we zoom in, we see again here the salty water, we see here the ice crust, there are these vents, these cracks in the ice crust, and on top of the water table, we believe that organics accumulate, and ascending gas bubbles then burst on the surface and create this kind of sea spray aerosols. And they can then, these nucleation cores can then be used by water vapor to condense and to form ice grains and to be injected into space and in the end detected by Cassini or the CDA instrument. Now, I've talked a lot about Enceladus, and we also have to make a case for Europa. All right. Yeah, we have ongoing chemistry due to charged particle radiation on Europa's surface. We have these evidence for plumes on Europa. And the interesting thing here for life is that we think that if we have these charged particles and we have chemistry on the surface due to this, this is oxidizing. And any reaction between a seafloor with a liquid water is supposed to be reducing. So we might have oxidation on the surface and reduction on the subsurface. If we now somehow can connect this, we might create a redox potential. And the interesting thing here for life is that all terrestrial life that we know from Earth is based on such redox potentials. So we just have to connect somehow we just have to connect these reduction and oxidation somehow. And for this, yeah, and we believe that there might be some processes ongoing in Europa's ice crust, some kind of solid ice convection that lead to upwelling interior structures. We might have some subsumption, that's another word for subduction. So definitely Europa is geologically active. And there's also a possibility that we have some lakes or kind of water pockets in these in this ice. So chances are not bad that we can somehow create a redox potential within Europa. Okay, and to summarize again, our lab work, we can interpret recorded flight data by using our lab experiment, but that's not all. We can also, in theory, predict each and every substance. We can just measure each and every substance in our lab and predict how future flight data should look like if these substances are incorporated in ice grains and encountered by these SUDA-type instruments. And that's what we did. For example, we measured amino acids and fatty acids. So you don't have to understand each and every single signal here, but what we see again, these blue diamonds, these are peaks from the water matrix that have nothing to do with the amino acid, but you also see the parent molecule protonated. You see different typical fragments of the amino acid together with some nitrogen species here. And for the case of fatty acids, we have mixed abiotic abundances and biotic abundances into solutions, measure them with our setup, and we can clearly differentiate between these two substances. So in the abiotic case, you have different fatty acids that have equal peak heights. So and in the biotic case, you have a clear dominance of even carbon number fatty acids. So the carbon number is here labeled above the peaks, for example, C16 or C18 here. And we even detect dimers. Dimers means that you have two parent molecules sticking together, and these are then detected. And until this point, so we always bought these compounds, mixed them together into solutions and measure them. And the next step is then to see what about real living things. So could we even detect, let's say, these biosignatures? So, and now, so we went to bacteria. If you ask biologists that you want to start working with bacteria, and I'm not a biologist, but if you ask them, they most likely recommend you a good starting point might be E. coli. Yeah, and that's what we did. We also decided for E. coli in the beginning. So this bacterium is it's rod-shaped, about micrometer, 2 micrometers in size. It's part of gut microbiota, where it where we benefit from it by producing vitamin K. It's the most finely studied organism on Earth. It's fast growing. And if the animation works, then you can see here a growing E. coli culture. It's mesophilic. This means it likes moderate temperatures for growth, and it is able to adapt to various ecological conditions. And in addition to E. coli, we've also chosen another microbe for our investigations, and that's Sphingopyx alascensis. It's a very ultra small microorganism. So it has a volume of less than by Enceladus, for example. It has been isolated from several marine permanently cold environments. So it likes cold stuff, cold environments. This is also what psychrophilic means. And it is also oligotrophic. So oligotrophic do not need too many nutrients. Yeah. And for size comparison, I just put quickly E. coli here in, and you can really see the difference in size of these two bacteria. So all these listed properties here of these S. alascensis bacteria make them a better potential organism for an icy moon like Enceladus or Europa than E. coli is. And what we then did is with these bacteria, we extracted DNA, we measure DNA. So I will not explain it in each and every detail, but you have your cell culture, you centrifuge it, and you have your cell pellet, add some stuff to it, and centrifuge again. In the end, you can dilute it in water, and then you have DNA in nearly pure water diluted. It's a very small sample volume. In the end, we can inject it into our setup and see what happens. If we can see characteristic signals of DNA, just in case we would encounter something like this in these ice grains. And what we see is first on the top right, you see the typical DNA molecule consisting of 4 nucleobases. That's adenine, thymine, guanine, and cytosine. And these nucleobases are held together by the phosphate deoxyribose backbone. That's a phosphate sugar backbone. And again, here you have a very, very busy mass spectrum. That's an anion mass spectrum, negatively charged ions of 100 to 150 ppm by weight DNA. You see signals from the background solution, from the water that was used to dilute the DNA. And you can also see the interesting peaks here are yellow, marked yellow. These are phosphates and phosphites from the phosphate sugar backbone. And you can also see here in green, these are characteristic fragments from the DNA. So these are these nucleobases. You can see adenine, you can see guanine, and tentatively thymine. And if we measure the same solution in the cation mode, it's basically the same story. You can also detect characteristic nucleobases. So again, here adenine, guanine, also cytosine here at mass 112, for example, also some fragments of these nucleobases. So if you always have different peaks from the same substance, this really supports your theory that you have really found this substance in your mass spectrum in the end. Okay, that was E. coli DNA, but we also wanted to analyze DNA from the other bacterium, and the problem was we could not find the same, we could not use the same extraction kit, probably due to the lower cell volume or so. So we had to find another one, and we gave it a try. We found concentration of 3 to 4 ppm by weight. That's much, much, much lower, but we wanted to give it a try. We just injected it into our setup and measured this stuff. And so we could not detect something at these concentrations in the cation mode, so positively charged ions, but we found still in the anion mode negatively charged ions, and we clearly see still these nucleobases. And this concentration of 3 ppm is really, it's pretty low. It's 100 times lower nearly than we measured with E. coli DNA. Then I also told you that we have salty oceans of Enceladus, and we also know that Europa's ocean is salty, so we have to add some salts into these DNA solutions, and see the effects and investigate the effects of salts in the solution, because they might suppress the signals, or we don't know what happens if we add salt to the DNA spectra. So when we do this, we added 10⁻³ molar sodium chloride. We see that we still have a similar spectrum, but with slightly lower nucleobase peaks here in different colors. If we increase the salt concentration, we see more and more peaks from the sodium chloride background, but we still see the nucleobases. And once we add too much sodium chloride, we don't identify these nucleobases anymore, but we see peaks from the sodium chloride background. And then in addition to DNA, we have also analyzed lipids from membrane lipids. So we have used a very old method to extract these lipids. Basically, you add chloroform, methanol, water to your sample, and you incubate a bit. Basically, you wait, and then you add again some water and chloroform, centrifuge, and in the end, you have a biphasic system with an upper phase containing polar molecules in a mixture of water and methanol, and then you have the lower phase containing chloroform and lipids. The chloroform is then removed by an airstream, and you have a solid cloudy stuff in the sample, and that's your lipids. You then dissolve them, and then we can measure them with our setup. That's what we did first for E. coli again. And what we see more even carbon number fatty acids than odd carbon number fatty acids, so it means more red than green here. And you see also some of these unsaturated fatty acids, and most abundant is C16 and C18. And this is exactly what you expect from terrestrial life on Earth, from bacteria on Earth. And if we then do the same with these Alaskensis bacteria, you see quite some differences. So in addition to C16 and C18, you have C15 fatty acid, very abundant. You have a few more unsaturated fatty acids. These are these bluish peaks, bluish labeled peaks. Then you have also fatty acids with very, very high carbon numbers, C22 or C28, for example. And it's possible, but it's really unusual. So we can definitely differentiate between these mesophilic E. coli bacteria and psychrophilic, cold-loving S. alaskensis bacteria in lipid spectra. And after showing you the lipid master figure, I know the last thing I want to talk about is now moving from extracts to whole cells or lysed cells. So could we detect with instruments like CDA or SUDA whole living, or maybe not living, but whole cells in these ice grains? And if such a scenario even makes sense for an icy moon, for this, to tackle this question, we need some theory. And for this, we first leave Enceladus and Europa, and we go back to our own planet, to Earth. So our ocean represents a big, big habitat for bacterial cells. And we know that on Earth, around 40 to 80% of all cells, they reside in biofilms, such as the Newton. This is a very tiny microlayer on top of the oceans on Earth. And we know that cell densities in this microlayer are 3 to 5 orders of magnitude higher than in the surface, than in the bulk water phase. We also know that organics and cells in this microlayer can serve as, again, nucleation cores for ice clouds. And this looks then like this. So we have the surface microlayer with organics and cells on top of the ocean. Then you have ascending gas bubbles. That's just Earth. That's a process known from Earth. Gas bubbles that ascend and that burst on the surface, create sea spray aerosols, and just by wind get transported, or and when temperatures get colder, then you can form ice clouds. So there is a process on Earth to use actually bacteria or organics to create icy stuff, to create ice grains. And now we move back again to Enceladus. And there is already an existing concept for an organic microlayer on top of Enceladus ocean. We believe that there is this organic solid microlayer on top of Enceladus ocean that is then we have these gas bubbles that are ascending. And because of Enceladus' low gravity as compared to Earth, these gas bubbles are probably bigger, and this bubbling, these bursting process is a bit more efficient than on Earth and generates organic solids that are then again coated by water ice, ejected into space, and can be detected by such instruments like SUDA or other future instruments on Enceladus or Europa. And we can now put bacteria into this microlayer that are then also lifted by this bubble bursting process, serve as nucleation cores, and these bacteria are then incorporated in ice grains and ejected into space. And we now need some calculations for this in order to simulate such a case in our lab. So we have a typical radius of Enceladus ice grain of 0.5 to 2 micrometers. And if you know that, you can calculate the volume of this ice grain. And then you use one cell as nucleation core, and you pack one cell into this ice grain, and you end up with a cell density that is shown here about 10 to 10 or 10 to 12 cells per milliliter in the end. So when we want to simulate such a case in our lab, we need similar cell densities or even lower cell densities, because if we use lower cell densities, then we might simulate a worst case scenario. So if we detect biosignatures with lower cell densities, then the chances are pretty good that we also see signatures at higher cell densities. And that's what we did. So we mixed such a solution. We used these Kansas cells that would fit into the ice grains, used a bit lower cell density, and just injected it into our setup. And we saw and then we received such a mass spectrum. So that's a cation mass spectrum again. You see that's a bit not so spectacular at the first glance. You see water signals, you see sodium signals, you see ammonia signals. These signals might come from the bacteria, but this is not a biosignature. If you just have some kind of ammonia or sodium, but it is a bit more interesting when we zoom into the spectrum. So that's actually exactly the same spectrum, just zoomed in between mass 80 and 180. And based on all our previous experiments, we find amino acids. We find arginine, glutamic acid, aspartic acid, and lysine. And we do not only detect these parent molecules, we also see fragments of these amino acids. So there's a good case for amino acids. We also can assign a peak to deoxyribose, which is the sugar of the DNA, together with fragments and water clusters. And if we measure the same thing in the anion mode, so negatively charged ions again, first we see a big peak at 146, which can be assigned to glutamic acid, which makes sense because we have the same amino acid in the cation mode. And but what is a bit more interesting still in the negative spectrum is this fatty acid pattern. We still see 4 peaks that can be assigned to fatty acids from the membrane of these bacteria. And for this, I want to remind you on the lipid extracts that I've shown. So the 4 highest peaks in the pure lipid extract spectrum are 241, 255, 269, and 283. And these peaks in very similar abundances are also seen in the anion spectrum of the whole cell material. So this is actually a pretty cool result. And with that, I just summarize quickly my presentation. That's my last slide I have. So icy moons are among the best places to look for alien life in the solar system. So we also have Mars, also Venus gets more and more interest. And we know that ice grain analysis on Enceladus or Europa provide a cost-effective means for analysis of subsurface oceans. So as compared, for example, to a lander mission. So you just need to fly through the plume and you can detect these ice grains and you can analyze the subsurface ocean, and you might even detect some kind of life, or you can find something that tells you, yeah, we don't have life there. For flight data, for analysis or prediction of flight data, we definitely need laboratory analog experiments. And these experiments have shown that biosignatures of bacteria could be identified by a pseudotype instrument down to the ppm level if these biosignatures are incorporated in ice grains. For example, we see nucleobases from DNA or lipid. Spectra show characteristic fatty acid abundance patterns. And we also see signatures of single cells in individual ice grains that could be identified. Yeah, thank you for your attention.